Okay, we're gonna review the work of Eddie Oshins, who's a critical originator of non-commutative quantum biology. And I discovered a fellow in Brazil who is working on his PhD in quantum biology, and he relies on this model of torsion vibrations, and torsion is also the model that Claude Swanson used, and it seems similar to non-commutativity in quantum physics, but it's not quite the same. And Eddie Oshins explains the crucial difference, but you really have to study Eddie Oshins. And fortunately, he provides us with a visual explanation, which makes it a lot easier to understand the concept. So first of all, we will look at the quantum biology work of Rick Saw, discussing what he calls a tensegrity based biofield tissue matrix. So this would appear to be very similar to the non-commutative approach, because he's talking about a vibrational coherence between phonons and solitons that's bidirectional and non-local. So the problem is that he's using a Fourier transform without realizing that the process is non-commutative as non-locality. And so we need to explain in detail why that's an important difference to understand. And so I sent him an email with these links about Eddie Oshins to help him understand non-commutativity. First of all, I looked up a couple other studies that are similar, more recent work on the de Broglie-Bohm model. So here you have another new study showing that indeed there's this non-local non-locality of spin that's demonstrated. But again, the question is, what does that really mean? So this was just demonstrated recently, an experimental test of non-local energy alteration, March 21st, so just a couple months ago. So again, you have a corroboration of the alteration as a non-local correlation through the spin corroborating the de Broglie-Bohm theory. Quantum correlations could enable the non-local alteration of energy distribution. Okay, so we are getting corroboration again, and we need to understand what this means on a deeper level, because the de Broglie-Bohm theory was analyzed on a deeper level by Basil J. Hiley. So we will be getting into Basil J. Hiley in relation to Eddie Oshins, because they make very much the same point, which is pretty awesome. So when we cite the papers of Eddie Oshins when he was working at Stanford Linear Accelerator Center, he points out that non-commutating operators of quantum mechanics relate to different objects on a macro scale, in contrast to non-commutativity in classical physics relating to the same object. So that's an important difference. You have two different objects for the non-commutativity of quantum mechanics, but in non-commutativity in classical physics, they can relate to the same object. So why is that true? And so, again, out of the mathematics, the non-commutativity is order dependent, based on the observables, and so in classical physics, the non-commutativity is based on the position and the spatial frequency. But in quantum physics, the non-commutativity is the position and the momentum, which is related to spatial frequency through Planck's constant. So basically you have frequency is to time as momentum is to wavelength as position. But because of that Planck's constant, you have a deeper level of non-commutativity that is between two different objects as position and momentum, because momentum has mass instead of just position and frequency, because frequency refers to just not just mass but also just energy as like light waves. Okay, so he's pointing out that this is why the neuroscientist Carl Brebrem was wrong to claim that Fourier transform could just be applied as a holographic model of the brain that's equivalent to Bohm's quantum hollow movement, because this term hollow movement was coined by Bohm after the use of the term process. So they were trying, Basil J. Hiley explained that David Bohm and Basil J. Hiley were trying to explain this non-commutative process, and so then they used the term hollow movement, but that got misunderstood as being a classical hologram, which it is not. So Eddie Oshins tried to explain this to Brebrem, but Brebrem couldn't understand this deeper difference of the quantum non-commutativity. And so Eddie Oshins says that Bohm did not, Bohm knew this difference, that holograms were classical, but that quantum physics requires that any measurement is non-invertible, irreversible act of amplification, decoupling the observer from that which is observed. Now, what's fascinating about this point of Eddie Oshins is that it's before the weak measurement experiments. So what the weak measurements experiments were able to do was to isolate just one of the objects being observed. So whether it was position or momentum, they could isolate it, and then they could do the amplification of that one object before you had the strong measurement that was the non-commutative decoupling of the observed from the observer. So that weak measurement process then could prove that the non-locality is inherent to the reality between the two objects that normally would have to be considered inherently decoupled by the measurement process, what's called the quantum measurement problem. So that's what makes the Bohm quantum potential model such a profound model, as Basil J. highly emphasized, is because of this. This inherent non-commutativity is actually going on before the uncertainty principle is enacted as the amplification process for the position or of the particle. So you can prove that the momentum is inherently non-commutative because the time and frequency are inherently non-commutative, and the frequency is directly proportional to the momentum. So then Eddie Oshins goes into the matrices mathematics, and of course his whole point was to relate this back to the paradoxes in psychology, which is what made Eddie Oshins' work so brilliant, is that he realized that just as Heisenberg had discovered the inherent non-commutative algebra logic to the spectroscopy of the emission and absorption of photons and to electrons, and this same non-commutative algebraic logic could be applied to psychological interactions and logical paradoxes. So matrices have the property that the multiplication is order dependent, and so Max Born realized that the Heisenberg symbolic multiplication was nothing but the matrix calculus that he had known actually from a work on electromagnetic, what's the book? Anyway. So the matrix multiplication is not commutative. So in quantum physics, there's a measure of the difference of such ordering, and that's what's called a commutator. And that commutator is precisely the measure of the interaction between the measuring and the measured system. So that's what the identity matrix is. And Basil J. Halley's point was that what von Neumann proved was that the Schrödinger wave equation is equivalent to the Heisenberg matrices mathematics up to the identity matrix, but that there's this deeper level of non-commutativity that's going on as non-locality that David Bohm had discovered as the quantum potential. And that's what Basil-J. was focused on. So because of this inherent non-commutativity, the quantum states have a projective, linear, and usually unitary, that's again this identity matrix representation, and therefore a fundamentally different principle of superposition than the classical physics. So again, in classical physics you have this superposition, you have the position and the spatial frequency do not commute, but in quantum physics it's the position and the momentum that doesn't commute. Because you're relying on the amplitude, the squaring the amplitude to get the momentum, and it's that squaring process that is what causes the non-commutativity through the Planck's constant as the energy. And so again, what David Bohm and Basil-J. are proving is that there's a deeper level of non-commutativity before that amplitude squaring process. And so again, Eddie Oshins is emphasizing this non-commutativity. So the great thing is he explains it with these images instead of just the matrices mathematics, because obviously most people learn visually. So if we look at the images, he's explaining this rotation of 90 degrees and so he's saying that when you add these two rotations from A to B plus B to C, it equals the turn to C to A. So why does it equal that turn? Because you have the inherent change of direction from B to C but you're going back to A in the mathematics. And so this is precisely what Heisenberg discovered as the truth of the transition, what he called transition frequency, and what he also called the order of the overtones in the spectroscopy of the Ritz-Rydberg combination principle. So the two turns are equivalent if they can be superimposed by displacing either one along the great circle. Okay, so go back to this. So the turns form a group under addition. In analogy to vectors, the sum of two turns is defined by addition. This addition is non-commutative. So the turn has a zero length if you realize the identity because it's inverse. In other words, if you just go one direction and then reverse it, you're back where you started. And so when you're in a 3-parameter object, then the turn has an inherent order to it, and that's why it's a spinor and not a vector. So it's an impenetrable object. whereas the torsion is a non-commutative two-parameter object that's a point spinner and not a finite size spinner. So that's the difference between the torsion that is being claimed by Rick Saw as a point spinner instead of a finite size spinner in three-dimensional space as an impenetrable object. So this is also what's called the Dirac dance, and he relates this directly to Neigong. Here you have a double covering of palms as found in martial arts, a Bagua and Silat, and it's the Philippine wine dance. So this is what Luke Hoffman made a video of this that got posted on YouTube, and he did this with Eddie Oshins. He got that Philippine folk dance from Eddie Oshins. And Eddie Oshins, in turn, got it from my own quantum physics professor, Herbert J. Bernstein, right here. So I learned this in 1989 before Eddie Oshins learned it, which is pretty funny. Okay, so well, actually, Eddie Oshins might have learned it around the same time. So here he is again doing the Bagua, and he's comparing that turn to the same spinner represent circumnavigation. So he says this is also found in Wing Chun. So basically he's saying that the outside of the hand is yang and the inside is yin, and the upper body is yang and the lower body is yin. And here he's talking about how he developed this with Luke Hoffman. The quaternion handshake, and they made a video about that. So let's get back to that. Here we go. Okay. So if you have them be directly opposite points that are equivalent, then that would mean they're scalar. And then when you have them return back to their original point, that's the identity matrix. Okay. And then he's also comparing it to the Tai Chi Quan exercise called the silk reeling exercise, which I have on my blog as well. Let me see if I have this for. Here it is. This is the silk reeling exercise. This is the same thing as the Dirac dance that I learned in my quantum physics class taught by Herbert J. Bernstein that Eddie Oshins then cites in this paper, showing the spinorial orientation and entanglement relation. So that's the secret of quantum physics that he calls the physics of Tao. So it's super wild. So here, this is what was in the Luke Hoffman video. This is the Filipino wine dance. So basically you have the outer hand, outside of the hand is yang, and it goes to the lower body, which is yin, and then the inside of the hand is yin, which goes to the upper body, which is yang. Okay, so this is the deeper non-commutativity in the double slit experiment from the weak measurement. So you have this in the double slit experiment, you get these waves, and they can't figure out, because if you send one single particle, they know that it forms a wave, and they don't know why. And Richard Feynman said there's no way to understand that, but if you study the quantum potential of David Bohm, they figured out there's this non-commutative momentum, which is the equivalent of the frequency, the non-commutative time and frequency. So this is from the future as a negative frequency, but it's in the imaginary axis, and because it's in the imaginary axis, it's this horizontal guidance to the particle, and this is happening at the same time non-locally, and you can prove that through this weak measurement experiment. So what okay, this is the guy who did this experiment. He also worked with David Bohm. His name's Yakir Aronov, and so he says there's a non-local exchange that depends on the modular variable. That's the momentum. I'm saying I now have an intuitive picture to understand interference by saying that when a particle moves through two slits, it always goes through one slit or the other, but it knows which other slit, the slit which it did not go, whether it is open or not, because there are non-local equations of motion. Finally making sense of the double slit experiment. So modular momentum. See, okay, it happens. Okay, I wait for the interference pattern to happen, and after it happens, I can check whether the particle was coming from this side or coming from that side by a future experiment. So if I'm able to describe the situation in the present by two vectors, one coming from the future that will tell me through which path the particle went, and one coming from the past that tells me that the modular momentum is definite, then I can see indeed that there's a non-local phenomenon. Okay, so let me get back to my blog post here. Let's see. Okay, so this image here is the crucial image that explains why the non-commutativity in quantum physics is inherently different than the classical non-commutativity, because as Basil J. Hiley explains, there is no point particle in quantum physics, that the non-commutativity is happening on this deeper level of the future and the past overlapping and affecting each other non-locally. So again, Eddie Oshins says the reader is cautioned that the type of wave interference that is relevant to a quantum context has nothing to do with the interference of physical fields such as light, as in holograms. Again, that's because of the non-locality. It's happening in pre-space, before space-time, so it's not a physical field.